Good afternoon, everyone. Today we are going to see about TS fuzzy control, an example, and fuzzy C means clustering. The outline of this talk will be as follows. First, we see TS fuzzy control towards an example of single link manipulator, where we can go for the regulation objective, where it has to come and settle down to a point for convergence. And then we have fuzzy control with optimal parameters. How can we have the fuzzy controller designed with optimal parameters? Then in the end of this lecture, we will be seeing the part which is fuzzy C means clustering. Now coming to the TS fuzzy control, the major difference between Mamdani type fuzzy control and TS fuzzy control type is basically the output is obtained by the linguistic variable in the case of Mamdani, whereas here the output is obtained through an expression or a model, precisely a linearized model. Because we know fully and thoroughly about the linearized models, we can get the non-linearized model. We can clearly observe the non-linearized model. Let us see an example that when the continuous TS fuzzy model of a single link manipulator whose dynamic model is given by x1 dot equal to x2 and x2 dot equal to minus g sin of x1 plus u is described by the 4 equations or 4 rules, because the 4 rules are the building block of a TS fuzzy model for the single link manipulator, where rule 1 states that if x of t is around the point 0 comma 0, then x dot of t is given by 0 1 minus 9.810 x of t plus 0 1 u of t. And rule 2 states that if x of t is around the point plus or minus pi by 6 and 0, then x dot of t is given by 0 minus 9.3710 x of t 0 1 u of t. The point x of t indicates x1 of t and x2 of t, that is 0 and 0. Similarly, for the rule 2, we have x1 takes 2 points, 2 values precisely, it is plus pi by 6 and minus pi by 6. With the linear model x dot equal to ax plus bu, where a is 0 1 minus 9.37 0 and b equal to 0 1 for these 2 cases. Likewise, rule 3 has the linearized model if x of t is around plus or minus pi by 3 and 0, then x dot of t is given by 0 1 minus 8.110 and 0 1 for B matrix. And these matrices A and B are obtained by linearizing this given nonlinear system by finding the Jacobian matrix dou f1 by dou x1, dou f1 by dou x2, similarly dou f2 by dou x1 and dou f2 by dou x2, with the point x of t equal to 0 and 0 transpose. With this, we get the matrix, Jacobian matrix, that comes to be the linearized matrix A for rule 1. Likewise, we can go for rule 2 by having the point being plus pi by 6 0, and we have one more rule corresponding to that with point minus pi by 6 and 0. So, we have a total of 4 rules given here, out of which 3 rules are having plus or minus, the equilibrium points being plus or minus pi by 6 0, plus or minus pi by 3 0, and plus or minus pi by 2 0. So, rule 2 again can be split into 2 and 3, and rule 3 will be 4 and 5, and rule 4 will be 6 and 7. So, total of 1 plus 6 equal to 7 rules here can be formed because of the equilibrium point given for the single link manipulator. So, now the question is to design a fuzzy regulator for this system. For that, consider that the local controller gains Kj, where j equal to 1, 2, 3, 4 for the rules given by, we have specified the k controller gains for these rules. Since rule 2 and 3 and 4 and 5, then 6 and 7, they do have same sort of k values because of that plus or minus pi by 6 comma 0 equilibrium point here, and plus or minus pi by 3 comma 0 point here, and for plus or minus pi by 2 0 for this k values. So, if I say this is rule 1 and this is rule 2 and 3, will take these k values. Similarly, rule 4 and 5 will take these two k values, that is k3. Likewise, rule 6 and 7 will take these. Okay, so we can consider a common Lyapunov matrix P equal to this, that is 1.6201, 0.4722 and 0.4722, 1.6201 in order to solve this problem, to design the fuzzy regulator. Okay, so now let us see the solution for this problem. The fuzzy regulator control law is represented by u of t equal to minus summation j equal to 1 to number of rules sigma j kj x of t, where kj is the local feedback gain corresponding to rule j, and or you know that number of rules here, it is 7, and sigma j is given by mu j upon summation of mu j, and the summation of sigma j for all the rules equal to 1, and mu j is a membership function corresponding to the variables associated with each rule. And it is considered that there are two state variables associated with this single link manipulator, x1 and x2, theta 1 and theta 1 dot, precisely joint angle and joint angular velocity. Here in this problem we have considered the theta 2, that is x2 angular velocity theta dot is 0 throughout the case. Next, coming to the pseudo code associated with this problem. So, the step 1 here is initialize the state variables, that is x1 of 0 is some value say 0.4 radian and x2 of 0 is 0 velocity, and the desired value x1d equal to 0 and x2d equal to 0.01. So, it has to come and settle down from 0.4 radian to 0 radian, and hence it is a regulation problem. Okay. And here is this pendulum. So, it has been perturbed by an amount theta, which is given by 0.4 radian, which is roughly around a 23-24 degree angle, and it has to be brought to the vertical 0 angle, because here theta equal to 0. This is the situation here. So, once we initialize the state variables, then we need to do this in discrete time. So, we have the sampling period assigned, let us say delta t equal to 0.01 second. Now, the step 3 is computing the error and derivative of error, E equal to x1 of 0 minus x1d, actual value minus desired value of state variable 1, and E dot is x2 of 0 minus x2d, which is equal to, we are finding it for the initial case. Then step 4, compute the membership functions for the input x1 and the output u for all the rules in this case, because your x2 is considered to be 0. So, let us focus only the input variable being x1 and u the output, in order to move further for finding the membership functions. So, for all the rules we are going to find the membership function values for x1 and u. So, for rule 1, x of t equal to 0, 0, and for rule 2 it is x of t equal to pi by 6, 0, and x for rule 3 x of t can be taken as, in my case I have taken like this. We can also take rule 2 pi by 6, 0, rule 3 can be minus pi by 6, 0, but I have taken the positive after the 0. So, rule 1 is 0, 0 point, and rule 2 pi by 6, 0, rule 3 pi by 3, 0, and rule 4 pi by 2, 0, and rule 5, rule 6 and rule 7 are for minus values, for minus pi by 6, 0, minus pi by 3, 0, and rule 7 minus pi by 2, 0. Now, let us talk about the rule 1, which is given by, where the rule 1 corresponds to the membership function of the variable x1, that is given by the Gaussian membership function. Okay. So, that is given by e power minus x minus b whole square divided by root 2 sigma, where x is the variable here, it is x1, and b is the mean value, and sigma is the width of that, or the membership corresponding to the crisp value x1. So, we have obtained for x1 for the initial case, for rule 1 we have obtained membership function of the variable x1 being 0.8521. Likewise, we have obtained for rule 2, rule 3, rule 4, rule 5, rule 6 and rule 7. Okay. That is the case. Okay. So, we can say that minus pi by 3 and plus pi by 3, this is it. So, this is the Gaussian function that we have taken, Gaussian membership function, one around plus pi by 3 and another one around minus pi by 3. That is how we have obtained 7 rules from the given 4 rules data. Now, step 5 is control outputs for each rule, and this part is the subpart of the rule. As say rule 1, if x1 of t is around 0 and 0, then u1 is given by minus kx. So, deliberately I put kx first, and in the end I can do minus continuously or commonly for expressing the minus k of kx as the control value. So, I have taken u1 is k vector multiplied by the x, where x is x1 and x2. So, for rule 1, u1 is k1 k2 associated with k1, small k1 k2. So, that is multiplied by minus 8.6628 x1 of 0 plus 0.6422 multiplied by x2 of 0. Likewise, rule 2, rule 5 will have the same k, and rule 3, rule 6 had same k, and rule 4, rule 7 had same k. So, we got accordingly the values of the control signal for, or the output signal for each rule. Next, having obtained the consequent of each rule, now we need to have the defuzzification value that is obtained through weighted average defuzzification formula or approach. So, step 6 is final output of the TS fuzzy logic block, that is the defuzzification approach to get the crisp value from the fuzzy values, that is precisely using weighted average defuzzification method, that is given by u equal to summation I equal to 1 to number of rules, say 7 ui ri upon summation I equal to 1 to 7 ri. That leads to u1 r1 plus u2 r2 up to u7 r7 upon r1 plus r2 up to r7. So, for the first iteration we got u, that is the crisp value obtained from the defuzzification block is 3.0963, and this u value is given back into the discretized state model in order to obtain x of k plus 1, that is x of k plus 1 equal to x of k plus delta t into x dot of k. Okay. So, in that case we can say that the x1 of 0 plus delta t equal to x1 of 0 plus x2 of 0 multiplied by delta t, which is equal to 0.4. Position, new position equal to old position plus old velocity multiplied by time step. Likewise, for x2 we have obtained this, which is minus 0.0080. So, after completing the entire simulation or the iteration has been completed, in order to have the error tolerance, then we have obtained this system states time history with respect to time, where x1 is the position and x2 is the velocity. It starts with the initial value of the state x1, that is the joint angle being 23, and it converges to 0. Likewise, the initial velocity also converges to 0. Even though it starts from 0, there are some initial intermediate perturbations and then it gets settled down. The control input associated with that is shown here. It starts with 3.2 and settles down to 0 in the end, since it is a regulation problem where the control input becomes 0 in the end. Now, let us move into the second topic of this talk or lecture, that is fuzzy control with optimal parameters. Let us consider there are two inputs, E, that is error E, and derivative of error E dot, and one output variable U, where these three are called linguistic variables associated with fuzzy control: error, derivative of error, and the control output. The corresponding linguistic variables are considered as precisely the membership functions associated with the fuzzy subsets of these linguistic variables are negative, 0, positive. So, the negative fuzzy subset will have a triangular function varying from A1 to A3, and the 0 subset of the fuzzy linguistic variable error E varies from A2 to A4. Likewise, the triangular membership function of the fuzzy subset P, which is positive, of this variable, linguistic variable E, error E, varies from A3 to A5. Now, these values for each membership function, triangular membership function, must be optimal. That is the objective here. Likewise, same thing is repeated here for another linguistic variable, which is derivative of error E dot, which also has the fuzzy subsets negative, 0, and positive with the membership triangular functions having the boundaries P1, B3 for fuzzy subset or membership function for negative, and 0 membership function has B2 to B4, and positive membership function has B3 to B5. Likewise, the control input or the control input U has the membership function, triangular membership functions for fuzzy subsets N, which is negative, 0, and positive with the varying parameters, which are nothing but the variables C1, C3 for negative case of negative membership function of U, and for 0, C2 and C4, and for positive it is C3 and C5. So, there are design variables which are 5 plus 5 plus 5, 15 design variables for this optimization problem. To find the optimal values for these 15 design variables, an optimization technique can be used, precisely a global optimization technique, which is genetic algorithm, can be utilized. For that, we need an objective function. So, given the pseudocode for this fuzzy control with optimal parameters goes with this technique, pseudocode, give the minimum and maximum values for all the design variables associated with each membership functions A1, A2, A3, A4, A5, similarly B1 to B5 and C1 to C5, so that we have a constraint set on these design variables, that each design variable will have the maximum and minimum range associated with that. Now, initialize the parameters associated with optimization technique. Start the main for loop. Inside the main for loop, we have two important sections or parts, you can say. The first part is fuzzy logic control algorithm, It can be either Mamdani based fuzzy or TS fuzzy model, and find the fitness function whose value has to be optimized or minimized for each set of the parameters. So that it states that with these constraints, with the maximum and minimum values associated with the 15 design variables, we can find the u value, that is control input, and that control input given to the system model, that is a state space model, and obtain the system response, get the error, and that error is the objective function which has to be minimized at each design variable set. So, finally, we come to see that at what design variable set, that is entirely searched within the design variable space, which optimal value had the minimal objective function will be chosen as the optimal design variable set, and accordingly each membership function with the ranges A1, A2, A3, A4, A5, accordingly B4, B1 to B5 and C1 to C5 can be assigned for each membership functions. So, there is a total of 5 plus 5 plus 5. So, 15 membership functions with these design variables. Now, select the optimal parameters based on the minimum fitness value. Therefore, the output of this code are the optimal parameters associated with the linguistic variables. So, the output of this optimization approach will give the optimal design variables. Using them will lead to fuzzy control with optimal parameters. Now, let us move on to fuzzy C-means clustering, which is similar to Martinez proposed approach. A researcher in the early 90s, he has proposed coherent self-organizing map in neural network scheme, which is an unsupervised learning technique. Fuzzy C-means clustering is also similar to that. First of all, let us discuss about clustering. What is clustering? Clustering is an unsupervised machine learning technique that groups data points based on their proximity, closeness to one another, forming a specified number of clusters. When I say clusters, there are two types of clusters. One is hard clustering and soft clustering. Let us talk about hard clustering and soft clustering. Hard clustering is a technique in which the data point is associated with only one cluster strictly. For example, in k-means clustering, here we assign each data point exactly one of the k-means of the k clusters by minimizing the sum of the squared distances between the data points, by minimizing the Euclidean distance between them and their respective cluster centroids. Thus, strictly each data point belongs to only one cluster. Whereas, in soft clustering, as the name indicates soft, each data point may belong to multiple clusters with varying degree of membership grades. The degree of membership or the membership grade differs, allowing for overlap between clusters. In the case of hard clusters, each data point here like this, whereas in terms of soft clustering we have this. So, the data points here belong to multiple clusters. For example, in fuzzy C means clustering we have soft clustering, which means the data points belong to more than one clusters simultaneously. Now, the algorithm associated with this fuzzy C means clustering is, first step is initialization. Initialize the number of clusters C, so as to decide how many clusters we want to find in our assigned data. Second is choose the fuzziness parameter M, and this parameter determines the level of fuzziness. And then third initialization is towards the membership matrix, and this matrix contains the membership grades for each data point in each cluster. Obviously, the membership function value is in the interval between 0 and 1, and the sum of the membership grades is equal to 1. So, step 2 is calculate initial centroids. Calculate the initial centroid, that means the cluster centers. In case of 3D it is 3D data points, it is centroid. In case of 2D data points, it is center, using the membership matrix that is given by Vi equal to summation over k equal to 1 to n uikm multiplied by xk divided by summation k equal to 1 to n uikm, where Vi is the centroid of the cluster I and uik is the membership grade of data point k in cluster I, and xk is the data point. Now, step 3 is update the membership function or membership matrix precisely. So, update the membership values of each data point and each cluster using the formula uik equal to 1 upon summation over j equal to 1 to c dik upon djk power 2 upon m minus 1, where uik is a membership grade of data point k in cluster I, and dik is given by the Euclidean distance between xk and Vi, and djk is the Euclidean distance between xk and Vj, where Vj, Vi are the centroids. Now, step 4 goes for recalculating the centroids using the update membership matrix that is given by Vi equal to summation k equal to 1 to n uikm multiplied by xk upon summation k equal to 1 to n uikm. Repeat this step until the centroids do not have significant change. That means the change in centroid is less than a very minimum tolerant value. Step 5 is recalculate centroids. Iterate between updating the membership matrix and recalculating centroids until the algorithm converges. The convergence can be determined when the changes in the membership matrix and the centroids fall below a certain tolerant value. Step 6, which is the final step, assign data points to a cluster. Once the algorithm converges, assign each data point to the cluster with the highest membership grade, so that they are assigned to that cluster. So, the summary here is initialize, which means choose a number of clusters, fuzziness parameter, initialize the membership matrix, 3 steps associated under initialization. The second step is calculate centroids, compute initial cluster centroids based on the membership matrix, and then third step is update membership, and fourth step is recalculate centroids, and fifth step iterate, repeat steps 3 and 4 until convergence, which means a change in centroids and the membership matrix entries can be almost equal to 0. And finally, assign clusters, assign each data point to the cluster with the highest membership grade. Let us see an example, quick example, that segmentation of a 2D image or 2D map. So, our objective in this example is to segment a given 2D map. So, in that case an unsegmented map containing all the detailed information including noise and fine grained variations in terrain or features is used to represent the environment with all the intricacies and variations in data is given, which is a nothing but a original image, let us say. And here comes the segmented map, which simplifies the original map by reducing the number of distinct regions to the number of clusters defined. It highlights the main regions or features, making it easier to identify and analyze. And this is helpful, the segmentation is helpful in applications such as path planning, obstacle avoidance in robotics. Again, let us follow these same steps in order to have the segmentation of the given 2D map. First is initialization, start by defining the number of clusters, the number of clusters, initialize the number of clusters and the fuzziness parameter. Simultaneously initialize the membership matrix with the random values, ensuring each data point's membership values whose sum equal to 1. Step 2 is load and pre-process the map data. Load the map data, typically a 2D array where each cell represents a different terrain type of or obstacle, and reshape it into a 2D array where each row represents a point. Given the pre-processed map being an alpha cross beta array, this new reshaped map becomes an one dimensional array, which is nothing but alpha beta into one array. Alpha cross beta has been reshaped into alpha beta array. So, that 2D data becomes a one dimensional data. And then let us start the fuzzy C-means clustering approach here. That means iteratively update the cluster centroids and membership matrix until convergence. So, compute the centroids with the expression given by Vi equal to summation k equal to 1 to n uik m into xk upon summation k equal to 1 to n uik m, where m is the fuzziness parameter and uik is a membership value of kth data point in the reshaped map, which is an one dimensional array of dimension alpha beta into 1. Then update the membership matrix according to the following formula, which is uik equal to 1 upon summation j equal to 1 to c djk dik upon djk power 2 by m minus 1, where uik again is the membership grade of data point k in cluster I, and dik is given by the Euclidean norm between xk and Vi, and the jk is Euclidean norm between xk and Vj. Repeat the process until the algorithm converges. Step 4 is post processing, that is after convergence assign each data point to the cluster with the highest membership value, reshape the data back to the original map, and we get our segmented map. That means first we had 2D becoming one dimensional array, then we process this fuzzy clustering algorithm, then finally convert back into the original 2D array. So, the further analyzation is with the segmented map given here in the left hand side, which is in the given the unsegmented image, we can have the output of this approach. Fuzzy C-means clustering gives you this, the segmented image, so that we can easily obtain our features, where are the obstacles, so that we can go for the path planning approach clearly. Thank you. With this, I end up this talk. Thus, we have seen an example of fuzzy TS fuzzy control of a single link manipulator towards a regulation problem. Then we have seen how can we approach the fuzzy controller with optimal parameters. Then fuzzy C means clustering has been studied in this lecture. Thank you.